Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for week number 8 of our course of communication systems. In our last lecture, we started discussion regarding the probability theory because in many cases we have to deal with random signals, and that analysis require some implementation of the probability theory in the practical scenarios. So we are continuing our discussion related to probability. There is one type of probability which is named as conditional probability. We know that probability gives a chance of occurrence of any event. Conditional probability also gives chance of occurrence of an event. However, this chance of occurrence is calculated on the basis of information that another event has already occurred. So, say for example, if we have two events A and B, so we want to find the probability of A. So this conditional probability, which is written like this, probability of A with this vertical bar, and B, so which is read as probability of A given B. So this probability of A given B is actually calculating the probability of A, where we know that B has already occurred. So information of occurrence of B is there. So you know that B has already occurred, and on the basis of that information we are calculating the probability of A. So this conditional probability is actually defined by this mathematical relationship here, that probability of A given B is probability of A intersection B divided by probability of B. Of course, this formula is valid whenever probability of B is greater than 0. Yeah, that means it should not be equal to 0. And of course, if probability of B becomes 0, in that case conditional probability does not make any sense, because conditional probability is calculated when B has already occurred. So if probability of B is 0, that means B will never occur, and we cannot calculate conditional probability. So this is the conditional probability, which is calculated for an event whenever we have information regarding occurrence of another event. This A intersection B, probability of A intersection B, is generally called joint probability, because this gives you the probability when both A and B, they are occurring together. So they are actually based on the common occurrence of both events A and B. Similarly, we can define the probability of B given A. So this one shows that we are calculating probability of B where we have the information that A has already occurred. So if we want to calculate the probability of B on the condition that A has occurred, in that case that will be given as probability of A intersection B divided by probability of A, and likewise it has to be calculated where probability of A is greater than 0. From this relationship, if you multiply this PA here and you multiply PB here, you can see that this PA intersection B is common on both sides. So we can combine this relationship in this form. Probability of A intersection B can be defined as probability of A given B into probability of B, or probability of B given A into probability of A. Sometimes in problems we have to reverse the condition. There are situations in calculation where you have to calculate a conditional probability on the basis of another conditional probability. So if we know the probability that probability of B given A, if we know that, we can calculate the probability of A given B. You can see that this relation comes from this relationship here. Probability of A given B can be calculated by simply dividing probability of B onto the other side. So probability of A given B can be written as probability of B given A into probability of A divided by probability of B. This relationship is named as Bayes rule. So Bayes rule actually enable us to reverse the condition whenever need arises. There is another important theorem in probability which is named as total probability law, which is actually gives you the probability when an event depends on many other events. So if, say for example, an event A depends on other events B1, B2, B3 and so on, B up to Bn. So if we want to find the probability of event A, the total probability of event A, so we have to include all the possibilities. So what is the probability of A when the B has already occurred on the condition of B1? What is the probability of A when B2 has occurred, when probability of A when B3 has occurred, and so on. And you can see that this is a weighted sum. For each term has been multiplied by the respective probability of occurrence of that conditional event, which is the first term has been multiplied by probability of B1, second term is multiplied by probability of B2, and third term is multiplied by probability of B3. So you can see that total probability law states that if we want to find total probability of A, we have to find the weighted sum on the probabilities of their conditions, and we have to find weighted sum of the conditional probabilities weighted on the probability of individual conditions. Another important concept related to probability is related to independent events. So if we have two events, say A and B, they are called statistically independent if they do not depend on each other. So if they do not depend on each other, in that case these events are named as independent events. That means occurrence of A does not affect occurrence of B, or occurrence of B does not affect occurrence of A. You can see that if the events A and B are independent, that means their conditional probability will not change whether the event has occurred or not. As I mentioned, that independence means occurrence of any event does not affect other event. So if we want to find the probability of A given B, so probability of A given B will be same as probability of A. Actually probability of A shows the probability when B has not occurred, and probability of A given B shows the probability when B has already occurred. So you can see that when these events are independent, so occurrence of B does not change the probability of A. Similarly, occurrence of A does not change the probability of B. So if we want to find if we want to check the independence of event, in that case the conditional probability of B given A would be same as the probability of B. In that case these events will be statistically independent. However, from the definition of this conditional probability, you can see that if the events A and B are independent, in that case probability of B given A would be equal to probability of B, and if you multiply this probability of A with this on this side, you can see that probability of A intersection B would become equal to the product of A, probability of A and probability of B. So there is another form of determining whether events are independent or not. That determination is made on this conditional probability, that probability of A intersection B should be equal to product of individual probabilities, probability of A multiplied by probability of B. If this condition is satisfied, in that case the events are said to be statistically independent. Otherwise the events are not independent. Similarly, if there are three events A and B and we want to check whether they are independent, in that case we have to check all possible possibilities with this condition, that they are pairwise independent. That means the probability of their intersection is equal to product of their individual probabilities, and they are independent as a whole, like the probability of their entire intersection should be equal to probability product of probabilities of individual events. So these conditions are more easy to incorporate in mathematical analysis. So for typically for independent event, generally we refer to this condition that their probability of their intersection becomes equal to the probability the product of their individual probabilities. At this stage I want to mention one more thing, that in our textbook has used another notation for intersection and union. The union has been represented as addition in our textbook. So A union B is actually written as A plus B, whereas intersection is represented as multiplication. A intersection B is actually written as A into B. So you should realize that this is just a notation to represent union and intersection that is used by our textbook. So A into B does not show the multiplication of set, rather it shows that you are calculating the intersection of those sets. Similarly, A plus B does not show that does not correspond to the addition of two sets A and B, rather they are representing that you are calculating union of those sets. So these are independent events. So let us try to take up a simple example in order to understand the concepts related to this probability theory. So we consider an experiment of tossing coin 3 times. So we have a coin which we have tossed 3 times in that, and of course we are observing the sequences of heads and tail which are occurring in each toss. And of course you can see that because one toss corresponds to 2 possible outcomes, so for tossing coin 3 times we will be having 8 distinct outcomes. So the sample space would contain 8 sample points which are listed here: head, tail, head, tail, and so on. We have defined 3 events A, B, and C, which are defined below. That A is the event which corresponds to 2 heads. So if we get 2 heads in the toss, the event will be named as A. So if I ask you to identify what is the set A here, so here this represents 2 head, this sample point represents 2 head, this sample point represents 2 heads. So A would contain 3 elements which are listed here. A B event is defined as second toss differs from other 2. So the first and third tosses, they are same, and the second toss is different. So in that case you can see that this THT and HTH, they are representing those conditions where the second toss is different from other 2. So in that case the B would have 2 elements only, which are HTH and THT. C corresponds to the event that first 2 tosses match. We don't care about the third toss. So for first 2 toss, you can see that if we get first 2 heads, same head toss, or first 2 tails, the same toss in both cases. So this will corresponds to event C. In this Venn diagram here, I have illustrated the sets. We have a sample space which contains 8 elements, and out of those elements, these 2 head, tail, head, they form the set B. 4 elements, they form the set C, and these 3 elements, they form set A. HTT is not part of any event, although it is part of sample space. And you can see that from this Venn diagram, we can easily see that B and C, they are disjoint sets, so they are mutually exclusive, whereas A and C has a common element which is HHT. B and A also have a common element which is HTH. Okay, so this is our Venn diagram. So let us try to make some calculation. So if I ask you to find the probability of individual events P of A, P of B, and P of C, in that case you can see that the A contains 3 elements here, and whereas the S has total 8 possible sample points. In that case, the probability of A will be 3 over 8. The B has 2 elements and the sample space contains 8 elements, so probability of B will be 2 by 8. Probability of C, you can see that C has 4 elements, whereas the sample space contains 8 elements, so probability of C will be 4 by 8. So we can easily calculate the probabilities of individual events by looking at the Venn diagram as well as the sets notation for the events. If I ask you to calculate the probability of joint events, which are A into B and A and C, and recall that I just mentioned that A into B corresponds to A intersection B and A into C corresponds to A intersection C, and you can see that the both intersection the intersection of A and C contains just one element. Similarly, the intersection of B and A also contains just one element. So both intersections, they are representing only one element, so the probability will be 1 by 8. Whereas the probability of B intersection C should come to be 0, because we have previously seen that B and C, they are mutually exclusive, they do not have any common element, so therefore the probability of B intersection C, that should come out to be 0. If I ask you to find the probability of complementary event A, so complementary event of A is actually, its probability is given by 1 minus probability of A. So if you want to find the probability of A complement, in that case that will be A into 1 minus 3 by 8, which comes out to be 5 by 8. If you want to find the probability of union of A and B, that is A plus B, in that case the probability of A union B would be probability of A union B should be equal to probability of A plus probability of B minus probability of A intersection B, as we have previously discussed. So if we substitute all these values, probability of A and B are 3 by 8 and 2 by 8 respectively, whereas the probability of A intersection B is 1 by 8. So if we subtract 1 by 8 from 3 by 8 and 2 by 8, it comes out to be 4 by 8. If I ask you to check the independence of events, you can see that this A and B, they are dependent event, they are not independent, because for independence we just discussed that for independence the intersection, probability of intersection should come out to be the product of individual probabilities. For A and B, we have calculated the individual probabilities which are given in the solution. We have also calculated the probability of their intersection. If I multiply this 3 by 8 by 2 by 8, you can see that the result would not be same as the intersection result. So you can see that the individual product, probability of A into probability of B, it comes out to be 6 by 64, which is not equal to probability of A and B. So from this condition we conclude that A and B are not statistically independent. Moreover, this independence is actually reflected from the conditional probability as well. If you calculate the conditional probability, you can see that probability of B given A is calculated as probability of A intersection B divided by probability of A, which comes out to be 1 by 3, and probability of A given B comes out to be 1 by 2. For independent events, we know that the probability of B given A should be equal to probability of B, whereas probability of A given B should be equal to probability of A. But in this case, we notice that this conditional probability does not is not equal to the unconditional probability. Therefore, we conclude that these events, they are not statistically independent. Let us take another problem here related to the statistical independence. We have a resistance R we want to draw this resistance randomly from a large batch having 5 possible values. So there are 5 possible values of resistances in the range of 40 to 60 ohm. The resistance of 40 has the probability of occurrence of 0.1, resistance of 45 has the probability of occurrence of 0.2, resistance of 50 has the probability of selection to be 0.4, resistance of 55 has probability of selection to be 0.2, and resistance of 60 has the probability of selection to be 0.1. Let's say we define an event that the selected resistance is less than or equal to 50 ohm. If we want to find the resistance which is probability of A which is less than or equal to 50 ohm, you can see that this condition can be satisfied with 3 possibilities. Either the resistance is 40 ohm, or the resistance is 45 ohm, or the resistance is equal to 50 ohm. I have emphasized the word or because in set notation, whenever you have the concept of or, that means you are having the concept of union. So this ORing is actually represented by union in the set, and as 40, 50, 40, 45 and 50, they are also mutually exclusive. So you can easily calculate the probability of their union by simply adding their individual probabilities. So probability of occurrence of 40, probability of occurrence of 45 and probability of occurrence of 50, they are added together to calculate the total probability of occurrence of A. Similarly, we have defined another event which shows that the probability of which is defined as B, that chosen resistance is between 45 and 55 ohms, and of course it contains 3 possible values, 45, 50 and 55. So its total probability comes out to be addition of their individual probabilities, which is actually 0.8. Okay, if I ask you to find the probability of intersection of A and B, the intersection of A and B occurs at 45 and 50, because this 45 ohm resistance and 50 ohm resistance, both they are included in the definition of A as well as in the definition of B. So the probability of their intersection comes out to be 0.6 by simply adding the probabilities of 45 and 50. You can see that if I multiply 0.7 with 0.8, that is the probability of A is multiplied by probability of B. So this multiplication comes out to be 0.56, which is actually not equal to 0.6, their intersection. So the intersection probability is not equal to probability of A and the product of individual probabilities. Therefore, these selection of the resistance, they are not independent. So we conclude that the selection is not independent. We can use these relationships to calculate other probabilities as well. For example, if I ask you to calculate the probability of A union B, you can simply calculate it by standard formula, that is probability of A plus probability of B minus probability of A intersection B, which comes out to be 0.9. Similarly, if we want to find, we can also calculate the conditional probabilities as given by the standard formula, and those probabilities comes out to be 0.857 and 0.75. Let us take another problem, which is actually very common problem in especially digital communication. This is a special channel which is commonly used and named as binary communication channel, illustrated in this figure here. You can see that there is a source which is illustrated by symbol X, and there is a receiver side which is illustrated by symbol Y. the source can generate two possible digits. Either it will transmit 0 or it will transmit 1. When this 0 or 1, it passes through the binary symmetric channel, this communication channel, of course it will be contaminated by noise, and sometimes noise causes error in the detection, and that error in the detection will result in a wrong decision at the receiver side. Say for example, if we transmit 0 at the transmitter side and it passes through the channel and we do not see any error, in that case you will receive 0. So 0 transmission will be received at 0 reception. However, if the error occurs, in that case we transmit 0, but it will be received as 1, because the error will make a error is made in the detection process. Similarly, if 1 is transmitted and there is no error in the detection, in that case this transmitted 1 will be received as 1. Whereas if there is an error in the transmission, so this transmitted 1 will be received as 0 at the receiver side. This transmission, they are associated with certain probabilities. So the correct transmission has a probability of Q0, whereas the probability of error is represented as P0 here. Similarly, probability of getting error, that 1 is transmitted and 0 is received, is represented by P1, whereas probability of no error for 1 is represented as Q1. So mathematically, this P0 represents that you transmitted y1, y as 1, whereas you received y as 1, whereas you transmitted x as 0. Similarly, P1 represents that you transmitted 1, x as 1, but you received y as 0. Similarly, Q0 represents the correct transmission, that you transmitted x as 0 and received y as 0. Similarly, Q1 represents the correct transmission, that you transmitted x as 1 and received y as 1. So these probabilities are given in the problem, that P0 is 0.1, P1 is 0.2, the probability of x0 is 0.5, means probability of transmitting 0 is 0.5. We know that the sum of probabilities in each case should come up as 1. So if the probability of transmission of 0 is 0.5, of course the probability of transmission of 1 would also be 0.5. So probability of transmission of 1 would be same as the probability of transmission of 0, which is 0.5. Similarly, as we know that the probability of error is 0.1 here, P0, so probability of error is 0, so probability of right transmission, correct transmission, Q0, can be calculated by subtracting this from 1. So Q0 would be 1 minus P0, which is 1 minus 0.1, which is 0.9. Similarly, for 1, probability of error, P1 is given as 0.2. So probability of correct transmission, Q1, can be calculated by subtracting 0.2 from 1. So Q1 is given as 1 minus 0.2, which comes out to be 0.8. So this is the overall situation here. So I just described what are the probabilities associated with these transmissions. These probabilities are sometimes named as channel transition probabilities, because they show that how the symbols will experience the transition when they passes through that particular channel. On the basis of these conditions, we have to find the following values. A part is we want to find probability of getting 0 and probability of getting 1 at the receiver side, means probability of y0 and y1. Similarly, there are other parts that we will be discussing afterwards. So let us start with the first part. you can see that the first part, probability of y0, actually y0 occurs in two cases. There are two possible ways where y0 can occur. First case is the one when you transmitted 0 and you receive 0 without error. So y0 will be received if there is no transmission no error in the transmission of 0. However, if 1 is transmitted and you get an error, even in that case you will receive a 0 here. So you can see that y0 would occur with two possibilities. Therefore, the probability of y0 should be calculated by total probability law that I showed earlier. Let me go back to that slide. So this is the total probability law, that if A occurs in different possibilities, so you have to calculate the total probability on the basis of this condition, that you have to make the weighted sum of conditional probabilities. So let me try to calculate here the probability of y0. The probability of y0 is actually occur with two possibilities: when you transmitted 0 and received 0, and the other possibility is that when you transmitted 1, x was 1, but you received as 0 because of the error occurring in the transmission. So you can see that there are two possibilities, and as the total probability law says this, you have to make it weighted average by multiplying with individual probabilities. So I have multiplied with the individual probabilities of x0 and x1. So this comes out to be probability of y0 given x0 is 0.9, as we have previously discussed. So it is 0.9. Probability of x0 is 0.5. Probability of x1 is 0.5. Whereas probability of y0 given x1, which is actually represented as p1, p1 here, probability of y0 given x1, so this one is 0.2. If you multiply and simplify, you would see that this comes out to be 0.55. Similarly, if we try to find probability of y1, so probability of y1 will be will occur, the y1 will occur with two possibilities, that is if we transmit 1 and received 1 without any error, that is with the probability of q1, or we transmit 0 but we received 1 with error, so it has a probability of p0. So again, this y1 also occurs with two possibilities, so we need to again use the total probability law. That is, first case, then that we received y1 but we transmitted x0. Second case, we transmitted x1 but received y1. And of course, as the total probability law requires to have a weighted sum, so we have to multiply it with the probabilities of px0 and px1. And as we know all the probabilities, py given x1 is q1, which is given as it is p0, which is given as 0.1 multiplied by 0.5, whereas py1 given x1 is q1, which is 0.8 into 0.5. So this comes out to be 0.45. Second part is that what is if a 0 is observed, so at the output, so y is actually 0, so y is 0, and we want to find the probability that 0 was at input state. So we want to find the probability that the input state was 0. So we are given that, so given condition is this output condition that you received a 0 here, and we want to find the probability of input side. That means we want to find the probability of input side of x0, whereas you are given that probability of y0 has already occurred, you receive 0 at the receiver side. So this is the case of conditional probability, because We are given a specific condition, and on the basis of that condition we want to find another probability. You can easily see that probability of x0 given y0 is actually not defined previously, but we have previously defined probability of y0 given x0. You can see that probability of y0 given x0 is given as q0 here. So this is known, but now we want to have the reversed condition probability, and whenever such cases arises, we have previously discussed that we have to use Bayes' theorem. So we can calculate this probability of x0 given y0 by using Bayes' rule, which states that this probability will be p of y0 given x0 multiplied by p of x0 into p of y0. As we have previously calculated all these probabilities, we can simply calculate it, which comes out to be 0.8818. The C part here says that if we observe 1 at the output, so we know that output is 1, so y is 1 is known, and we want to find that input was also 1, so we want to find the probability of having 1 at the input side. So we want to find the probability that input was 1, whereas we are given the condition that output received was 1. And again you can see that this requires reversing the condition, because we already know the probability of y1 given x1, so which is previously shown, probability of y1 given x1. So we can simply use Bayes' rule to reverse the condition, and if we apply that rule, that condition comes out to be 0.889. Now we come to the last part, which is calculating the probability of error. So what is the probability of error here? You can see that the error occurs in two possibilities. What are those possibilities? First possibility is that you transmitted 0 but you received 1. So this is an error. Transmitted 0 but received 1. Similarly, the other possibility is that you transmitted 1 but you received 0. So these are the two possibilities of getting an error. So since the error occurs with two possibilities, we have to apply total probability law in order to calculate the total probability of error. So probability of error will be given as two possibilities, that we transmitted 0 but received 1. First possibility, and second possibility is that we transmitted 1 but received 0. And as we know that for total probability law we have to calculate weighted sum, so we have multiplied with the individual probabilities of transmitting 0 and transmitting 1. So these probabilities are already known to us. You can see that p of y1 given x0 is given to be 0.1, which is p0 in the problem, multiplied by probability of x0 is 0.5. P of y0 given x1 is also given, it is 0.2, multiplied by p of x1, which is 0.5. So this comes out to be 0.15, which represents the total probability of error in this case. So you can see that with this channel transition probabilities, we can easily calculate all the probabilities associated in this problem. We can find the probability of getting each symbol at the output side. We can find the probabilities of error in this symmetric channel, and other probabilities as illustrated by these conditional probabilities here. So this concludes our discussion related to the conditional probability, independence, and other important concepts related to the probability. So we stop our discussion here. Inshallah, in next lecture we will be talking about random variables. Thank you all. Allah Hafiz.